So now we're ready to go ahead and determine the number of moles of each substance. So we know that we're going to have a number of moles of carbon and a number of moles of hydrogen. And I'm writing it like this for a reason. We'll come back to that in a second. Not sure what just happened there. Let me rewrite that. All right, so we have carbon and hydrogen. Really not sure why it keeps doing that. Okay, we should be good now. And then we know that the number of moles of carbon dioxide we're going to end up with is going to be the same as the number of moles of carbon. Looking back at our stoichiometry, the only product that has any carbon is carbon dioxide. So all the carbon in the reaction is going to end up as carbon dioxide. And then from there, we know that the number of moles of water, H2O, is going to follow the same story, where it's going to be the number of moles of hydrogen divided by 2. Right? And then we know we have methane, ethane, and propane. And we want the percentages of each of these because we're going to be multiplying it by our hydrocarbon ratios. So we're going to have an array, and it's going to be 95%, 4%, and then 1%. And this could change depending on what, whatever the actual mixture of your natural gases. So if we wanted to, we could make variables for these that you could change, but we'll just leave it like this for now, since we're only looking at one scenario. And we need to give this a name. And we'll just call it the fuel. And then we want to make another array that has our ratios of carbons and hydrocarbons because we want to be able to multiply or perform matrix multiplication to get the number of moles of each of these substances, which we can then use with our previous equations to determine the total enthalpy. So we're going to make another one, and we're going to call it, I'll just call it hydrocarbons. And we're going to make another array. This time we want it to be a 2 by 3, or 3 by 2. And we're just going to put in the number of carbons and the number of hydrogens for each of our elements. And we'll do it like this just to make it easier to picture. And then here we're going to have ethane, which is C2H6. And then we'll have propane, which is C3H8. So from here, we just need to multiply our fuel array and our hydrocarbon array, and that will give us the number of moles of our carbon and hydrogen. And actually, we will move this up a bit. Also, I did forget a set of brackets here. My bad. There we go. So let's go ahead and run that. So if we want to take a look at, say, our number of moles of carbon, so this is just simply the result of multiplying this times that, this times that, this times that, and then adding them together. So from here, we also need to include our number of moles of oxygen. Suggestive typing does get annoying when you're not trying to use things you've already defined. And then our number of moles of nitrogen. So we know our number of moles of nitrogen is just going to be equal to our number of moles of oxygen times our ratio, which is 79/21. Then our number of moles of oxygen is going to be equal to, and this is looking back at our stoichiometry, it's just going to be equal to our number of moles of H2O divided by 2. And then plus our number of moles of carbon divided by 2. Or not divided by 2, just times our number of moles of carbon. So from here we should be good. I keep using a 0 instead of an O. There we go. So this should give us our number of moles of each substance. The one thing that we need to add, though, is what happens when we put in excess air. And if we think back on what we talked about, any excess air is just going to go through the system, but we still need to include it in our enthalpy equations. So we'll say our excess is going to be equal to 0.2. And thinking back on this, any excess air that goes through the system is just going to need to be heated up, but it won't take part in the reaction. So to get our number of moles of oxygen, we just need to multiply by the amount of excess air we have. And then we don't need to do anything for our nitrogen because it's already defined in terms of oxygen. And since we're keeping a constant ratio of nitrogen to oxygen, we should be good. So now we're ready to determine the amount of moles of each substance we'll have in our input, in our output, or in our inlets, and then our flame. So we're going to start off by doing our inputs. The way we're going to do this is concatenating two lists. We're going to start with our fuel list and then also add in our other substances here. But let's start out by writing down our substances. And we're going to make an array out of these. We have a certain number of moles of oxygen and a certain number of moles of nitrogen. And we also technically have a certain number of moles of CO2 and H2O. If we were looking at this from like a truly scientific point of view, or we weren't making assumptions, there would be carbon dioxide and water, as well as like argon and some other things in our atmosphere or in the air that we're putting in. But in this case, we're going to assume there's absolutely nothing. We're only putting in oxygen and nitrogen. So we're going to say that there's 0 moles of CO2 and water coming in. Then we also have our fuel array. And all we need to do is concatenate these. And all that is joining two arrays along the same axis. I probably forgot a bracket somewhere. I forgot to put these in brackets. You need to basically say, I want this all as one big array. There we go. And then we can do the same thing for the number of moles out. We know that all of our hydrocarbons are going to be consumed because we have an excess of air. So we can put 0 for each of those. And then we want to do this in the same order we did it before. We have oxygen. So the leftover oxygen is just going to be whatever percent excess of air we have. And let me make sure I wrote that. Yeah, I did. I wrote that down correctly because the corresponding number of moles of oxygen is going to be consumed burning the hydrocarbons, but whatever's excess is going to be left out. And then, of course, none of the nitrogen is going to be consumed. And then we're going to be left with some CO2 and some H2O. So let's go ahead and check that. So now we basically just need to use this this function right here with these values and determine the enthalpy of reaction. So now we're on the home stretch. We need to make one more equation. And we'll call this the delta H equation. And we're going to input this as a vector so we can use the root function later on to solve for the actual output temperature of the flame. And in this, we're going to say that the temperature is going to be equal to the first index of our vector. And all we needed to do Actually, I'll leave the return for now. We're going to take the dot product of our enthalpy function up here and each of these values in our two input and output arrays. And the reason we're doing that is because we want to find the enthalpy released by each of these substances throughout the process, or the amount of energy that it takes to heat them, depending on if it's positive or negative, and then also the amount of enthalpy that they came in with. And then we can take the difference between those two, and that'll let us solve for the output temperature of the flame. So again, we have our number of moles in of each substance. And actually, I'll just write it like this. Numpy dot, and we want to take our h of t, or our h t. And again, t, or temperature, is just going to be the first index of the vector that we put in. And we're going to be taking the dot product of that with the number of moles in. And the dot product is just multiplying each element of the array by ht. So from here, we want to do the same thing with the output stream. And we have same thing, our enthalpy formula and our number of moles out. And that is what we want to return. Forgot a colon here. All right, let me double check this to make sure I didn't screw up any parentheses. Looks good. And then from here, all we need to do to solve this is find the root of this function here, and that will tell us the temperature of the flame. And actually, this is not. There we go. That was not accurate before. All right, so we want to take the root of our flame temperature, and the vector we're going to be putting in is our initial guess. I need to run this again. There we go. Oh, well, going all the way back up here, I forgot to specify numpy functions. Python doesn't have these functions built in. You need to import something, in this case numpy. Okay, so that might be the reason why. So let's try c divided by np tanh. And the reason the hyperbolic cotangent is the same as 1 over the hyperbolic tangent. All right, there we go. So this is our output flame temperature. And to get just that, we want to take the first term of our output array. So the answer I had before was wrong. Actually, it's closer to 2063. And the one error I made, actually 2 errors I made. First off, I had n in and n out flipped, so obviously don't do that. The other thing I forgot was that these values up here for our heat capacity were in terms of joules per kilomole. So to get it in terms of moles, we have to divide by 1,000, and that significantly changes our answer.